So yeah, welcome to the second lecture. Today we will talk about robot control and Markov decision processes. We also have received some feedback from you for the first week. It turns out the first homework assignment was maybe a little challenging, so we've extended the deadline for that. We've also created a Moodle forum where you can ask questions and see if other students have asked the same questions that our TAs will also try to help and answer. And we have also made the slides and recordings available in case you didn't receive the password to access the content. Here is the login details that you need, and this will be the same for the future. And yeah, so let's get started for today. So we'll start talking about robots, because one of the most exciting things about robot learning right now is the diversity of the hardware we are dealing with, right? So you've got everything from quadrupeds navigating in outdoor terrain to dexterous hands solving Rubik's Cube, drones flying, and so forth. And you know, from the distance, this looks like completely different problems, right? Like trying to control all these different robots, right? And so the core question is like, how do we actually control these very different morphologies? Because all of these robots have this different like joints and actuators, and different physics, but they all, you know, kind of share the same fundamental constraint that we want to translate some sort of high-level goal into specific motor torques required to move that specific morphology throughout the world. And to build this kind of general foundation model for robotics, we can't just like try to solve it for one robot, but we have to understand the underlying framework of robot control that applies to all of them. And so looking at all these different robots from the last slide, how do we find a common language to describe what they're actually doing, right? And it turns out that most of them, almost all of them, you can describe as a collection of rigid bodies transforming or moving through space. What this means is we assume in this mathematical framework that the robot is a rigid body, meaning that the distance between two points on the robot remains constant. So this means that it doesn't like squish or stretch while moving. And one of the benefits of this is that we essentially only have to track one point on the robot instead of like multiple. And so here on the left, you can see how this would look like for like a planar motion. So if you have like a car or like a robot that's like navigating on the ground, you would describe it, this would be like mostly represented by its motion in X, Y, and maybe like an orientation. And so you would describe this using like the SE2 group, so the special Euclidean group. And it's kind of simple, but you know, it's like the fundamentals for like ground motion. Now for something like drones, this would that live in the full 3D world, you would describe this with SE3. This is spatial motion. And so here now you add like a Z for altitude and also like 3 rotational axes, roll, pitch, and yaw. This is probably like familiar with most of you, but just to kind of go through the basics again so everybody's on the same point. How do we actually represent these in our code? We use homogeneous transformation matrices. On the left, you see this for the SE3, which is now 3 degrees of freedom, as we said, for X, Y, and then the theta. And we represent this with a rotation matrix built from sines and cosines, as well as a translational vector. And on the right side, you see kind of the equivalent for the drone or for the SE3, where we scale this to 6 degrees of freedom. And now we have like 6 values for the translation and 3 for rotation. And like maybe one thing to kind of like sanity check on the math here is that in order for these matrices to be valid rotation matrices, they have to satisfy two properties. First, the matrix needs to be orthogonal, so meaning that its transpose is equal to its inverse, and then the second is that it also needs to have a determinant of 1. And so this is not like, like a math trick, but just ensures that when when the robot rotates, it doesn't accidentally stretch or anything, so it remains a true rigid body. Okay, why do we care about all these matrices from the previous slide? Because in the real world, the robot typically doesn't have just one frame, but most probably a whole hierarchy of them. So look, for example, at this self-driving car example. So the car has a base frame where this is which sits at the center of its gravity, and which we use to kind of control and send commands to the motor, to the car. But then it will have some sort of sensor, like a lidar or a camera on top, sitting on the roof. And for example, now when the sensor perceives a pedestrian on the road, it will sense it in its local coordinate. And in order for us to, decide not to run over this pedestrian, we need to transform it back into our base frame where we are doing all the control. Now the beauty is that now we can chain all this homogeneous transformation matrices to simply do this conversions from where is the pedestrian in the sensor frame to where is it now in the base frame. And maybe a side note, actually, in order to, we will not cover this in this lecture, but in order to determine how, the transformation between the sensor frame to the base frame is, you would do this via sensor calibration, typically. All right. So far, we've treated robot as a single rigid block moving through the world. But in reality, robots are a bit more complex. For example, if you look at this humanoid, Lola, we will want to define this as articulated rigid bodies. So this means that this will have now 3 components. We will have links that are the individual rigid bodies, then joints that connect the links, and then end effectors, which are essentially for example, the gripper or the thing that you use to interact with the world. And the key takeaway here is that articulated robot is essentially just a chain of coordinate frames. So everything that we just covered, how to convert and chain all these matrices, you would do this to find out, for example, where your hand is relative to your humanoid's robot frame. You can just multiply and chain these to do these computations. Looking at robot arm articulations, here is how this might look for the Franca, a 7 degrees of freedom, very popular kind of robot arm, as well as the SO1 101. This is a robot that you will be using in the group projects later on. And you will see that, despite the right one being a much simpler robot, in principle, the definition is very similar. So from the mathematically, it's pretty much identical. Okay, so we talked about how the arm moves, but motion has to translate to interaction in the real world, right? And this happens with the end effector. There are different types of end effectors that one can use to interact with the real world. I highlighted 3 different ones that are kind of common and popular in robotics. On the left, you see the suction gripper, which is, from a learning perspective, a very clean action space because it's binary. So it's either the vacuum is on or off. So you don't have to worry about any additional geometries. And this is typically used in industrial, pick and place kind of applications. Then in the middle is the parallel gripper, which is what you will find that most of the industrial robots that are like the Francas and the SO101s use that you will be using. Here, it's a 1 degree of freedom action, and you have to worry maybe about the width of the object, and requires a bit more precision to interact with objects. And then on the right, we have the dexterous hands, which are much more complex end effectors. So instead of just having like 1 or 2 degrees of freedom, you might have like over 20. And as we move into MDPs later, these are how these will affect how your action space essentially changes. Okay, maybe briefly I'll cover joints. So we've looked at the arm and hands, but so the joints essentially are like the mathematical constraint that limits the relative motion between the two rigid bodies, so that we can actually control them. Here is a diagram from like a modern robotics textbook. Well, you see like kind of the standard vocabulary of different types of joint. Honestly, pretty much the most popular joint that you should care about and that you will be using are the revolute joints, which allow rotation around a single axis like your elbow. All right. Let's talk about degrees of freedom. And this is starting to get to the core of why robot learning is so hard. So how do we count the total of freedom, the total amount of freedom that the robot has to move in space? We call this the degrees of freedom of the robot. And it essentially defines the number of independent parameters that you would need to define the exact state of the robot at any given time. And so here you can see how this is defined for these different types of joints. And in general, if you want to calculate how many degrees of freedom a certain robot has, you can use this formula, this Katzbach formula, where you start with the total number of possible dimensions of your rigid body, and then you subtract the constraints for every by every joint that you have added. Okay, now we need to talk about the space where all these parameters actually live. And we call this typically the configuration space or the C space. This is essentially the set of all possible configurations a robot can take. So looking at the table over here, you can see that the space depends entirely on the types of joints that you have. So for a point on a plane, it's simply like a Euclidean space. But if you look at the 2R arm, because it has 2 revolute joints, it's not going to be flat, but it will be a torus. And so this is kind of important because when we train our neural network to be a policy, the network has to respect like the different topologies that your robot configuration space has. So for example, in the torus case, so like the kind of the distance between 2 points is not always like a straight line, right? So if you're like at 356 and you want to get to 1, right, like the shortest path is like just at 2 degrees and not like going back like 358 degrees. Okay, so now the workspace. So we just covered the C space. Now we need to map this back into the real world. So the workspace is simply the set of all points that the robot can reach in the physical world. And so we make this distinction in robot learning because your agent will often live at in 2 different worlds at once. Like it will perceive the tasks in the workspace, like seeing a cup on a table, but it will have to execute the movement in the configuration space by turning its joints. And so this mapping is not trivial, as we will see in the next slides. Because there is also, for example, obstacles, right? For example, here, imagine in this like simplified kind of robot, if we have this blue circle that represents an obstacle, that would translate to this in the configuration space of the robot, right? So this is kind of the forbidden region that your, like robot joints should not reach. And it's important to understand that this is how roboticists used to do like motion planning in the 90s and in the 2000s. So the standard approach back then was to explicitly construct this like configuration spaces and like translate the obstacles into the configuration space, and then search for a path that stayed, like in the free space, as you can see in the next slide. Wait. Right, and so but this like effectively doesn't scale very well to higher, like the higher the dimensions of your robot. It becomes like pretty much like intractable to do these computations. And so in modern robot learning, we don't want to like pre-calculate all this like shapes and obstacles and have like perfect like structured world state. We want to kind of like have a policy that can like learn how to feel like where the obstacles are like implicitly, recognizing automatically that certain like actions will lead to regions of like bad outcomes, right? So this is kind of like the fundamental difference between hard-coded like geometry to learned representations that we'll be discussing in the rest of the term. Maybe to finalize this kind of definitions, let's talk briefly about the task space. The task space for a robot is essentially the manifold where the objective is naturally defined. So this is like independent of the embodiment. So for example, if the task is to clean this whiteboard, the task space will be all the surface of that, all the points on the surface of that whiteboard. And it doesn't matter if this is like a humanoid, a mobile single arm manipulator, or a flying drone that is going to like wipe the surface of that. All right. Question time. So now we've covered like quite a bit of concepts. So maybe to make sure that you all understand how these are applied, let's look at the Franca robot and maybe discuss with your neighbor for like half a minute or 20 seconds what the configuration, workspace, and task space could be. Okay, it's fine. Like we don't have time to figure it out. So the configuration space is yeah. Does this align? Does this align with what you thought?
It aligns. No.
Perfect score. Yeah, sorry about that. So yeah, we have the 7 degrees of freedom manifold for the configuration space. The workspace, as we said before, is like all the physically reachable space in X, Y, Z. And the task space will be like the 6-dimensional pose of the end-effector. Here you can see how the workspace looks. Maybe like one thing that is important that we will be covering now also is that because, as we discussed before, the task space is smaller than the configuration space, this leads to a redundancy and null space motion. So this means that, for example, if the robot is holding a mug of coffee, like perfectly still, there are many different ways for it to move the elbow while maintaining the same fixed point of the end effector in space. So this allows you also to plan around obstacles, for example. All right. We've defined our spaces. Now we need to cover how we move between them. So the most fundamental mapping is called forward kinematics. This is like answering the question of, imagine you already know all the joint values of your robot, of this arm. How do you compute where your end effector is, right? So given like all these 3 values, like where is like your end effector? And so this is a deterministic process. There's only like one possible answer. However, as we said before, this is not a bijective mapping because there might be many different configurations that lead to the same end effector. And this is why the inverse kinematics is a much more difficult problem because this is like the problem that we will mostly focus on in this course, which is, like our policy might predict a new target pose for our end effector, and we need to figure out which joint angles Q will get us there. This is essentially like inverse kinematics. All right. As I said, like the solutions in inverse kinematics are often non-unique, right? Like here you can see there could be like two very different set of joint angles that lead to the exact same end effector position. And so this is why for many complex robots there might not be an analytical solution at all to compute this. So in practice, oftentimes like we use some sort of optimization-based inverse kinematics where we define a cost function like the distance between the current pose and the target pose, and add some secondary constraints like staying away from obstacles and so forth that help us solve this with gradient descent. I will not go into too much details, but just kind of to get the gist of it, this is how, at the most basic form, such an optimization-based inverse kinematics would work, where we have this error between like the current pose and the target pose, and we want to like minimize this, let's say with a squared L2 norm of that error, and for then the update, and then we kind of iteratively apply this sort of Jacobian method that tells us like how a tiny change in each joint angle affects the position of the end effector in the real world, and nudge the joints until the end effector reach the target position. All right, so imagine we have now we have found, we have run the optimization and found a set of perfect joint angles that reach our target position. But like, how do we actually translate this into motion? Because the robot will just not teleoperate from one position to the next, right? So in order to move this, let's say we have the SO101 and we want to move it like 1 centimeter in like sideways in y direction, we will have to interpolate instead of doing this giant jump. So for this, we essentially want to create a series of tiny waypoints that will like move the end effector to the target goal. So this most simple way you could think of how to do this would be just doing linear interpolation, where we treat the joint space as a straight line. And so we also need to define a time, like what is the time we give like our controller to reach that end pose. And then we calculate how many waypoints or discrete steps we need to take. And then we just like interpolate, right? And so we care about this because, as I said before, like for the policy, we will have to like use some sort of like waypoint generations to like interpolate to the target poses our policies produce. However, there is an issue with this approach if we do this linear interpolation. And so while it's very simple and very easy to write down, it's actually pretty bad for our robot because this essentially means that, it will go to like full velocity at the first time step, and you see like this how this like velocity looks, and it will produce like a lot of stress also on the robot hardware, with also with this infinite spikes of acceleration, right? So it's going like full on, and then at the end it's going like from max speed to zero, like from one time step to the next, right? So that's like pretty bad. And so this is why typically instead of doing this, most controllers do something a little bit more sophisticated with like some polynomial-based methods, such as quintic splines. The idea is that instead of like doing like simple linear paths, you represent a trajectory of each joint as a fifth-order polynomial, and then you add like 6 boundary conditions to ensure smooth motion. And so essentially you encode that the robot should start and end with 0 velocity and 0 acceleration. So then the movement looks something like this. You can see like it's a much more smoother, like more gentle start, and also ends much more gracefully. And so that also like the Dirac delta spikes are now gone. And this is what a lot of waypoint generation methods like industry robots like Franca's will use. One last note on robot control. So now we have determined how we can generate like a set of joint configurations and waypoints to interpolate smoothly between them. But in the real world, the robot will never follow these perfectly just because you tell it to do it so, because there are like factors like friction, there is like gravity, air resistance, and so on, that will make the robot not follow like this waypoints perfectly. And so this is why typically you use like a PID controller to ensure that your robot is following this trajectory of waypoints as much as possible. I will not go into too much details. I guess many of you already have learned this in other lectures, but I try to visualize a little bit how the different components of the PID controller work when you actually try to follow a trajectory with the robot, right? And so you can see, for example, here how so the proportional is just like kind of proportional to the error, the target that you have between the desired trajectory and the one your robot is currently following, right? So the further off you are, the harder it will pull you towards the correct trajectory. And then you have the integral part, which will compensate, for example, for things like gravity. If your robot is very heavy and it's kind of like going down, it will kick in and pull you back up. And then, for example, if you overshoot, then the derivative will kind of help you dampen this and go back. All right. So now we know how to kind of this is a kind of a crash course on how we can actually affect motion with our robots on end-effectors, right? That's a very basic motion. And the question is well, are we now done? Well, obviously not, because in the real world, a robot needs to do more than just following a straight line, right? It needs to ideally decide which action to achieve or to take to achieve some complex, long horizon goal, especially when the world is unpredictable, noisy, or unmapped. And so we have covered kind of the control parts in robotics here. But now what we care more about in this lesson is the machine learning part. I'll take the questions at the end. Sorry. Essentially, for the decision making, to decide which is the next action the robot needs to take to achieve some complex long-term goal. This is an example, for example, from one of my previous works, where we were doing sushi cutting as a task with this bimanual Aloha robot. And so this is a very long horizon task where the robot needs to first grasp the knife with one hand, move it in the right position, then grasp it with the second hand. So it will do as you will see in a second, okay, it still vibrates a little bit, but, and this is very, very precise, kind of manipulation task, right? Because now it needs to go right. Okay, this is like a toy sushi. It's not real sushi, but it needs to go right in, in there. And that's like very, very difficult for a robot to do this like so accurately and precisely. And so this, for example, has like 14 degrees of freedom, right? It's like 2 arms, and it's like very high frequency. So it's like a lot of actions that your policy needs to predict at every point in time to decide how to do it. And then you have like the low-level controller, like the PID and all of that, that like ensures that the motor actually follow what your policy is predicting, right? So now we will cover like the basic mathematical framework that allows you to learn such data-driven policies to enable like policies to solve this sort of like long horizon dexterous tasks. Maybe let's first talk about how we can represent this mapping from observations to actions and introduce some terminology. This is typically not too different from how you might represent an image classifier, which maps from inputs X to some outputs Y, like for example here for this like cute cat with a neural network. Now a policy maps from an observation O, like here from this like camera view from like a car, from a snowy road to some output A, which in this case could be actions that tell the car how to drive, like straight, left, right, or backward. And so other than the symbols, like essentially not many things change so far, right? And we denote pi, the pi symbol, we use the pi symbol to denote the policy, and the subscript theta to denote the weights of the neural network of that policy. And so now, typically in a controlled decision-making problem, things exist in a temporal context. So like at an instance time in t, I'm looking at my camera observations O and with subscript t, and I will make a decision based on that denoted at. And then the next time step would be like t plus 1 and so forth. And in this course, we will use like integers time steps, which starts at 0 and then go 1, 2, 3, and so forth. But in the real world, there could also be like some sort of continuous notion of time, such as like milliseconds, for example. And so mathematically, as I said before, a policy is just a conditional probability distribution over actions given an observation. But there is a big difference here. In classification, if you mislabel a cat as a dog, the cat doesn't change. But in robotics, if your policy chooses the wrong action, the state of the world changes. So if your car turns left into a ditch, the next observation that the network will see will obviously be very different. And in the most general case, policies provide distributions over actions. So they will assign probabilities to all different actions, which we will call stochastic policies. But there are also special cases like deterministic policies that assign a probability of 1 to a single action and 0 to everything else. So we have defined a policy, but what is the policy looking at? And so here it is important that we distinguish between states and actions. So, for example, looking at the car here on the left, like the state is like the ground truth. Let's say it's like the exact position of the car on a map, its velocity, orientation, and so forth. And then on the right, this would be like the observation, right? So, like the observation is produced by a state, and this is like some sort of like a lossy mapping, right? The key insight here is that like no matter what is the weather or visibility, even if it's like like a snowy, like night driving, like the observation might change, right? Like the amount of information you're perceiving from like the sunny, clear skies to this, like very bad visibility driving, but the state doesn't change. So the state remains constant. It's always the same. And so this is important because, like in robotics, we typically operate with observations, like images from cameras that will give us like partial information about the state of the world. In the language of probabilistic graphical models, we can describe this as the following. The policy pi will give us the conditional distribution of A given O, and then the state and the action together provide a probability distribution over the next state, and this will call the transition function or the dynamics wall. And maybe one thing to note here is very important, maybe some of you already have heard, this is the Markov property, which means that if you are trying to determine state 3, so S3, and you already know S2, then knowing S1 doesn't provide any additional information that helps you determine S3. And this kind of makes sense because, as we said, right, like the state already contains all the information you need about the world. So knowing the past doesn't help you determine the future. But still, even though you might know the state, predicting the future might be difficult due to stochasticity. Maybe to confound you a bit more, in this class we will mostly use the terminology of S for states and A for actions, which goes back to dynamic programming of the 50s and 60s with Bellman and so on. But you might have seen, for example, in the example I did for the PID control, that sometimes people also use the notation of X for actions, X for states and U for actions, which comes from kind of optimal control theory. But this is essentially the same. Maybe the only thing you should know is that for rewards and cost function, you have this inverse relationship. Whoops, sorry. All right. So now the Markov decision process. This is the formal framework that kind of summarizes everything we'll be talking about, from motor torques to high-level goals, and is defined by this tuple over here with the state space, action space, the transition probability, and a reward function. And the reason why the MDP is fundamentally so important is that it provides us some sort of unified mathematical framework that allows us to treat complex physical machines exactly like any other computational agent, enabling us to apply the same learning algorithms to a 27 degrees of freedom like humanoid robot as we do for playing the game of chess. Okay, so for the state spaces, there are two different categories. This can be discrete or continuous. So for the discrete ones, for example, in a game of chess, there is no halfway between squares, right? So you have to you can kind of see everything. For the continuous state spaces, this is what we will use mostly in robotics. This will be for example, the joint angles, and these are defined by real numbers. And so this matters for robot learning because in a discrete world, an agent can essentially explore by trying every different buckets in its state space, while in a continuous world, there might be an infinite number of states. And so you cannot just build a table for every possible states and its value, but you have to use function approximators and neural networks across this infinite possibilities. Similarly, talking about action spaces and how they influence the world, we have again the same categorization between discrete. This could be for example, the keyboard. If you're controlling the robot in the simulator with the keyboard, this would be discrete action space. While if you use, for example, a VR motion controller to teleoperate it, this would be a continuous and much smoother action space. Regarding the transition model, in a perfect world, our transition model would be deterministic, as shown in the left. So this means that if we command our car to turn the steering wheel exactly 5 degrees, the car would move in a perfectly predictable arc. But in the real world, there is stochasticity. This means that the road might be slippery, there might be ice, there might be, I don't know, the tires are worn out, and so you might not get that exact predictable behavior. And this is why in robotics we often use this stochastic transition model modeling. Right. For example, with the arm, it could be, as we said, that the motors overshoot, or there is like some uncertainty because of sensor noise and so on, that make like your robot not follow 100% like the trajectory that you're predicting. In MDPs, we also define reward functions, which model the behavior of the policy. This is mostly used in reinforcement learning setting or paradigm. Typically, most of you might be familiar. We can use either sparse rewards that only happen at the end of an episode, or if certain conditions are met, such as 1 if the robot like lifts an object and 0 otherwise. Or we can also use denser rewards, such as the Euclidean distance from like your end-effector to the point of the object that you want to grasp, which also accelerates learning greatly. And I have attached, the videos don't play, I have attached 2 examples from my PhD, where I was teaching an RL agent to do this kind of like pick and place tasks. And here you can see the difference that this might make when training like real world policies with RL for robotics. So you can see the sparse reward one like fails greatly, while the denser reward one can pick up the objects and place them nicely. Though I guess if we had trained the sparse rewards one like longer, it might eventually have learned it. All right. We have looked at the individual components of the MDP, the states, the actions, and the transitions. But the robot doesn't exist like in a single moment. It operates in sequences. And we call the sequences, or I already called them trajectories. And this is defined with this tau symbol over there. The trajectory probability represents the total probability of seeing a specific sequence of states and actions. So essentially, it tells us like how likely is a certain trajectory going to happen under the current policy pi. This is modeled by these 3 things. The probability, the raw is represents the probability of the robot starting at a certain state. Then we have the policy at every state, like what action does our policy choose. And then we have the transition function. So given the action, where does the physics actually land us? And so by multiplying these together for every time step, we get a complete probability of everything that could happen. Okay, now that we understand how to model a trajectory, we need to decide for how long should the robot care for in the future. And this brings us to the concept of the horizon. So there are like 2 categories, finite horizon MDPs, where a robot might have a strict time limit to execute this task, like let's say 5 seconds to pick a moving object. And once that is over, like the episode starts again. In this setup, the robot might change its strategy as it gets closer to the 5 seconds. So it could be, for example, learn like that second 4, it becomes more desperate and goes, for like a risky movement or something to achieve the reward. And then we have infinite horizon MDPs, which technically continue forever to infinity or until a certain terminal state is reached. And this is like more common in autonomous navigation or long-term kind of tasks. Maybe one thing to note here is that like in principle, just if you use like this formulation, like there would be no way for like the policy for the robot to know which policy is better if you accumulate like infinite rewards over time. And this is why we typically solve this with a discount factor, gamma, which you set between 0 and 1, to ensure that the rewards closer in time will get weighted more heavily than rewards in the distant future. Okay, this is the last slide. So putting all this together, how this is the learning objective to finding optimal decision-making policies. So first, you can look here. This is the accumulated reward an agent might receive for either the finite or the infinite horizon over its lifetime. So you can think of just like the sum or the discounted sums of the agent. But then, because the world is stochastic, like we model this as an expected return. So this average will return the average across all possible trajectories that can happen when we follow our policy. And then the optimal policy is the specific strategy that maximizes this expected return. Yeah, so it could be like, for example, this one over here. And yeah, I think with this we can switch to the paper discussions.